So let's now talk about the second area moment for different shapes. Here we see first what's called an I-beam, or often it's called an I-beam, but actually this is an S shape, or sometimes when they are wider they call it W shape, W for wide, but this here would actually be an S shape. However, engineers would always refer to this as an I-beam. And the I-beam is very good about bending about the strong axis, but not so good about the weak axis, right? I think we discussed that in the previous picture. Then I also have a channel here on the bottom left next to it. So that's called a C channel. So C channel. And then I have a pipe. And I have an angle. And I have a square tube or rectangular tube. Sometimes also pipe, doesn't matter. And now if you paid attention, then you might already be able to tell that some of these are very good for single directional bending, whereas some of them, for example the pipe and the tube, are very good about both directions or biaxial bending. So again, if I apply a force to this beam in this direction, the I-beam, that might be very good. However, if I apply a force in this direction, it's not as strong. Whereas for the pipe, for example, if I apply a force here and a force here, it is actually pretty much suited for that. And similar for the tube, that has very good strong and weak axis. In fact, the tube has no weak and strong axis. Both axes are identical. However, the angle and the channel, for example, they are very good about one axis, but not so good about another axis. So now let's look at real life pictures. Here on the top, we have 4 pictures of very common shapes. What you see here, for example, is called a Florida I-beam. This I-beam is like 1 Raphael tall. It's like taller than 6 feet from here to here. It's a very massive beam, Florida I-beam. Before we used Florida I-beams, we used what's called an Ashtow beam here on the bottom. Then we have a hollow concrete slab, and we have a double T girder or beam, depending on how you want to call it. But let's go through them one by one. So why do engineers build these? And the question that I most often get in the classroom is, hey, why do we not just create a rectangle? And the reason is due to what we already started talking about. So here is the centroid location, right? And remember that if there's a centroid location, there's also a centroid axis. So I'm gonna try to draw that into here. And so the bending over that axis is important. And what's very important is that you have a lot of material down here that is actually removed from, so I'm gonna simplify this a lot right now, but this material down here is very far away from the centroid location. And the further away you move this, the stronger the beam will be against bending. And that's why you can also see very long Florida I-beams, because they have a lot of material on the bottom, a lot of material on the top that is very far removed from the centroid. I mean, in all fairness, I need to tell you that there's also a lot of pre-stressing steel down here that is way beyond the purpose of this class. You should take classes like concrete design to learn more about that. But that is another reason why this beam is so wide here on the bottom, so that they can put a lot of pre-stressing steel in here. However, it is a good reason to move a lot of material down away from the centroid, and it helps the engineer to really provide a lot of resistance. And by the way, on the contrary, or in reverse, so all this material here that has been removed from the cross-section, that would be very close to the centroid location, and therefore it wouldn't offer a lot of resistance to bending. And so that's why engineers build these beams like this. Similar down here, this is like I said, the Ashtow girder. And the Ashtow girder has the same idea, right? So there's a lot of material here, bulky on the top, on the bottom, but nothing in the middle. And this one would be maybe even easier to be converted into a rectangle, but then we would have a lot of material here, and that would not be conducive towards carrying the loads. So let me just to bring that home also at the centroid location here, so that you understand that the material is far away from the centroid location. For the concrete slab here, the hollow slab is the same, so there was a centroid location right there. And what's the trick here? Same thing, the material here in the middle is not really helping. Remember that if the beam smiles, you have compression on the top, tension on the bottom, and so the material in the middle does not really resist that tension or compression, and so you don't really need it. And this is true for all these pictures here. In fact, it's also true for my double T-beam here. You see these double T-beams a lot in parking garage structures and so on. They are very comfortable structure components because they are very easy to fabricate, very easy to transport. And as you can see, they have 2 legs, so they never tip over. They are easy to store and they're easy to install. In fact, engineers use these like they use Lego blocks. And this is also true for all of these precasted elements. So these are precast concrete elements that engineers use as Lego blocks, but they are very much engineered to resist bending about the strong axis. And these do that very well. And engineers have used those and perfectionized those structures in many scenarios. Let me talk about the last thing here, again, in reference to the rectangular section. Why is the rectangular section not a thing? So we remove material, and one thing that I talked about the whole time here is that we do this to remove the material from the centroid location. That is number one. But we also remove material, and removing material saves cost and saves weight. All right, so you can imagine that these concrete beams are very heavy and they have to carry their own load, if you will, when they span from here to here. And so removing that material is really beneficial and saves cost. And so it's a win-win-win situation really for engineers, and this is why we use such structures and why we engineer structures in such a way. Okay, so now that we have a general understanding of the moment of inertia and where we want to go with this, right? So ultimately we want to be able to calculate the moment of inertia for such difficult structures, but before we do that, let's focus actually on simple shapes.